This experiment used numerical simulation of flow to evaluate the drag and flow visualization around the Millennium Falcon. The fluid phenomena of interest were the drag on the Millennium Falcon and the flow visualization around the Millennium Falcon. These phenomena are governed by the Reynolds number of the flow. We used three Reynolds numbers shown here for our analyses: 5.5 times 10 to the 4, 1 times 10 to the 5, and 4.6 times 10 to the 6. The Reynolds number was calculated by approximating the Millennium Falcon as an ellipsoid in the flow and using the long diameter of the Falcon as a characteristic length. The three velocities we used in our experiments are shown here. These velocities yielded the three Reynolds numbers that we used in our simulations. The other relevant parameters for the flow were also defined here. As you can also see, the dimensions of our model are included here, and these are in centimeters. We used the SolidWorks Flow Simulation package for our analysis. We used water at a normal temperature and pressure with three different initial velocities to match our three different Reynolds numbers. The fluid was applied at the front face of the fluid domain in the z direction, which will be shown on the next slide. For our convergence study, we ran the simulation with the smallest velocity at three different meshes: coarse, medium, and fine. Since the result converged at the medium mesh as shown in the plot, we chose to use it for our analysis. Here's a picture of the medium mesh we used and the fluid domain. The velocity of the fluid entered at the front of the fluid domain and continued in the positive z direction over the Millennium Falcon. To validate our simulation, we compared the results from the lowest velocity simulation to physical results obtained from a water channel. Using the same dimensions and flow speed, the simulation found the drag coefficient to be 0.317. This result is in the same ballpark as the experimental drag coefficient, which was found to be 0.125. The differences could have stemmed from the fact that the device which was measuring drag force in our experiment had difficulties picking up the small drag forces on the Millennium Falcon. Here is an animation of the visualization of the fluid velocity around the Millennium Falcon at a Reynolds number of 1 times 10 to the 5, or a turbulent Reynolds number. This is an animation of the visualization of the fluid velocity around the Millennium Falcon at a Reynolds number 1 order of magnitude above the last one, or at 4.61 times 10 to the 6. Here is a screenshot of the two velocity fields at the same location on the Falcon. As you can see, the boundary layer stays attached for longer at the second Reynolds number, which we would expect to result in a smaller drag coefficient. The wake is thinner for the first Reynolds number, which also results in a small drag coefficient. Although it is cut off, the wake for the second Reynolds number was also longer than the first Reynolds number. The results of measured drag coefficient versus Reynolds number are presented here. The drag coefficient decreased with the Reynolds number because of the thin wake and late boundary layer separation. In addition, coefficient of drag is proportional to drag force over velocity squared. The fact that the coefficient is decreasing with increasing speed means that the growth in drag force is not keeping up with the change in velocity squared. In conclusion, first, the numerical results did not match perfectly with our experimental results. And one of the possible reasons for that was that our physical model dimensions were not big enough for the water channel, which made it difficult to get accurate force readings, as I mentioned before. However, since our results were within ballpark of the experimental results, we feel that our results were valid. The drag coefficient of the Millennium Falcon decreases with speed, and the length of the wake increases. The boundary doesn't separate until farther down the Millennium Falcon as speed increases, which also helps keep the coefficient of drag low. With these results, it is clear that the Millennium Falcon is an effectively shaped spacecraft and will be able to handle high-speed travel without any problems with drag.